Here's how it'll work. First, you'll get an intro slide with the name of the presenter and the title of their poster. That'll be followed by a 5-second countdown, followed by the poster itself. Presenters, you get 1 minute. In the lower right-hand corner down here, you'll see a clock ticking. When your time's up, the next intro slide will play and we'll repeat the process. I think we have 23 or 24 people that are presenting today, so it should be pretty exciting. The only thing left to do now is get ready, because the poster slam starts now.
Hi everyone, I'm JQ from Kathy Arara's lab. Simply speaking, the question we want to answer is the high pressure effects and how high pressure affects on the biomolecules like proteins and RNAs. So why high pressure? So in structural biology studies, pressure as a method can help us look more locally into the structure and give more insights into the folding, unfolding mechanisms. And secondly, it's like over 90% of the microbial biomass on Earth lives under pressure. So we don't know much, we don't know much about their the structure of their biomolecules and any possible pressure adaptation of the sequencing function. So in our own lab, we have combined the high pressure with a lot of biophysical methods like MR, fluorescing, and high pressure stacks, which is the main focus here. So this is the glimpse of my poster. If you're interested, please come back to my poster, and thank you.
Nice.
Me now. Hi, I'm Yono-shin at Penn State University. I studied the mechanism of reiterative transcription, which is also known as transcript slippage, which plays an important role in controlling gene expression in bacteria. Using time-dependent shock trigger X-ray crystallography, I was able to watch RNA polymerase in motion in crystallog, which provided significant insight into the mechanism of transcript slippage. So if you are interested in learning this, please come check my poster at 5 p.m. Thank you.
Hi, I'm Robert Miller from Cornell University, and oftentimes the deep ocean is thought of as lifeless, where in reality a substantial portion of Earth's biology exists in the deep ocean under conditions of high pressure, and therefore there's a need for us to understand the role of pressure in biology. Furthermore, large industries such as food processing and pharmaceuticals rely on high pressure methodologies. Therefore, at Beamline ID7A, we've developed technology that allows us to access the gold standard of biosacks, or small angle X-ray scattering measurements, which are chromatography coupled sacks, which allows us to separate out different oligomeric species in solution while simultaneously collecting sacks data over a pressure range of about 0 to 100 megapascals, which represents the upper limit of pressures experienced in the deepest portions of the ocean. Our preliminary evidence suggests that pressure is a unique way to characterize biomolecules, and we're excited about the ability to explore the role of deep life in our evolution. Please come see my poster to talk more about it.
Hello, and thanks for coming. Later today, I will be presenting a poster titled Quantifying Microscale Drivers for Fatigue Failure via Coupled Synchrotron X-ray Characterization and Simulations. In this study, we combined high-energy X-ray diffraction microscopy with dark-field X-ray microscopy and a crystal plasticity fast Fourier transform model to investigate large gradients of intragranular misorientation and elastic strain near a twin boundary in a nickel-based superalloy. Here, in this image, we have a diffraction contrast tomography reconstruction of our extracted specimen featuring the grain of interest, its coherent twin, and a dark field X-ray microscopy scan taken directly below the twin boundary, which is a region well known for fatigue failure in nickel-based superalloys. I hope you can make it to my poster later today. Thank you.
Good afternoon, everyone. Our work is on iteratively manufactured metal matrix composites reinforced with ceramic particles. Cold-spray with different polarization conditions were used to produce our samples, where bonding between the two phases is achieved with high-speed impact. You can see typical microstructures of our matrix and reinforcements. Different microscopic stress-strain response was then was noticed when carrier gas was changed. So in order to understand our load partitioning between phases, we used in-situ loading and diffraction. We measured the phase-specific lattice strain from which load fraction and of the phases can be determined. And we hope to use these parameters to help us understand the load distribution, load transfer, as well as failure model in additive manufactured composites. You can discuss with me if you're interested in the data section.
As we know and have experienced, metals heat up and expand. Titanium alloys such as the Ti7Al being studied here have a hexagonal crystal structure. This structure means that the material is anisotropic or has properties which are different depending on the direction you're looking at. In this case, the material expands different amounts in different directions. Two samples of Ti7Al were heated up while far-field high-energy X-ray diffraction microscopy patterns were being taken in order to study the effects of this thermal anisotropy. The thermal expansion of coefficients and the ratio of the coefficients were found to be temperature dependent. It was also found that this anisotropic thermal expansion caused a change in the internal stress and strain state of the material as a function of temperature. Come to my presentation to hear a better explanation of my pretty pictures.
Hi everyone, my poster covers in situ characterization and modeling of cyclic deformation in rare earth magnesium alloys. The goal of the study is to analyze and predict the micromechanical response during low cycle fatigue, utilizing near field and far field high energy X-ray diffraction microscopy and crystal plasticity finite element analysis. Here are just a few quick highlights of what the poster will cover. The evolution of twinning, strain, and texture was captured for a single fatigue cycle with fully reversed loading. The Prism's plasticity, open source crystal plasticity finite element framework was then utilized to model cyclic deformation in the full three-dimensional volume as measured using near field high energy X-ray diffraction microscopy. And this joint HEDM CPFE analysis provides the ability to study a range of mechanistic phenomena, such as the mechanics of twin growth and the influence of grain size and texture within the sample. And if you're interested for more information, please come and view my poster. Thank you.
Okay.
Good evening, everyone. My name is Advaita, and I'm a graduate student in Professor Moridi's group at Cornell University. So my chess experiments were held this year in March at the Fast Beamline, where I studied the dynamics of metal additive manufacturing processes using X-ray diffraction at fast time scales. So for this purpose, we specifically created an AM setup. And in my poster session today, I'm going to talk about my experiments with Inconel at two processing regimes. One is when the laser is stationary and one when the laser is moving. So with my diffraction data, I'm going to establish major solidification parameters for additive manufacturing, and then I'll end it with a short discussion on evolution of the lattice strains. So please join me for my poster today. Thank you.
Hello, my name is Margaret Coker. I'm currently a visiting assistant professor at Lawrence University. I'm going to be talking about structural materials as well, but in a completely different application than you've seen so far in this poster session. My new project is going to be focusing on metal, primarily copper, and its use in cultural heritage items. So I made some preliminary measurements at what was formerly A2 long ago when the 6M Pilatus detector was brand new. And we're trying to look at how material develops in the process of making these copper drinking vessels. So I'll be talking about the traditional methods for how these bowls are made, how we might be able to study their material properties using X-ray diffraction, and what we might want to learn from that. And additionally, I'd like to touch on, if I have time today, how and why we incorporate undergraduate students into our research. Thank you.
Hi, I'm Peter Bocage from NIST, and my poster focuses on a program that we have in building the hardware to let us do machine learning enabled phase space exploration for liquid formulations. So we're working to understand things like nanoparticles, like even really simple systems like soap, water, oil, and salt can have incredibly rich phase behavior. And so we're using commodity robotics together with software that's pretty broadly translatable. We have these little widgets that are about $100 thing to get hardware onto a network so that you can talk to it from Python. And we've used this so far at Chess to generate these massive reference data sets for machine learning on Sachs patterns in complex materials. So the top right there is 500 Sachs patterns that were taken with 5 minutes of human intervention and about a shift of beam time.
Hi, my name is Stephanie Rosenblum from Cornell University, and I've been studying how the structure of polyurea changes under compression. So polyurea has been in use for over a decade as a coating to vastly enhance the blast and ballistic response of materials. However, the complex combination of high strain rate and high pressure associated with dynamic loading, such as that occurring from a blast, makes it pretty difficult to determine exactly what structurally makes polyurea so great at reducing damage. The result is that design of polyurea for specific new applications is often trial and error. To address this issue, we wanted to decouple the high strain rate from the high pressure response of polyurea. We did so using a diamond anvil cell to modulate pressure on a timescale that allowed for facile in situ structural characterization by Sachs and Wax. We anticipate that our findings will help direct a new predictive platform for the design of polyurea-based materials. If this interests you, please come check out my poster. Thank you.
Hi, this is Edward Trigg from the Air Force Research Lab. I'm going to be presenting a poster on characterizing the morphology of some 3D printed materials. So this 3D printing technique called direct ink writing has been around for a few years. And basically you're able to 3D print at room temperature a thermosetting material with fillers, such as carbon fiber, cure the material, and then you end up with a 3D printed part with good mechanical properties. So we did scanning microbeam X-ray scattering, both sacs and wax, on cross-sectioned parts. And in doing so, we were able to see the morphology not only of the carbon fibers from wax, which you can see on the right, but also of the nanoclay rheology modifier from sacs, which you can see in the middle. This is basically going to lead to improved characterization of these materials.
Hi everyone, I wanted to present to you all a high throughput technique that we've developed to identify structural transformations prior to beam time. We laser anneal thin film oxide samples, trapping metastable phases. And each anneal stripe is at most 1 millimeter across, so we're able to fit 625 anneal conditions on each 4-inch wafer and up to over 120,000 conditions across a composition gradient wafer. To analyze the anneal stripe, we collected both optical microscope images, reflectance spectroscopy, and then at CHESS, we collected spatially resolved XRD across the stripe. And what we found was that the conditions of materials transformations that we identified via XRD were the exact same ones that we could identify using the optical techniques, meaning that we can use those in-lab, inexpensive optical techniques as prior knowledge for searching processing phase space during beam time.
Hey everyone, so I use high-speed X-ray imaging techniques at CHESS to study the fiber alignment and resin flow behavior during 3D printing of composites. So there's been a lot of work over the last 5 years trying to improve the mechanical properties of polymer parts during 3D printing. And so one of the strategies to do that is incorporating carbon fiber fillers. The big question is how these fibers are aligned during the printing process and maybe how we can improve it or say control the fiber alignment during the printing process. So the magic happens inside the nozzle. So we use X-ray imaging techniques to directly visualize the flow of the fiber-containing resin. Now with that, we get a series of images that we can analyze quantitatively using a particle image velocimetry technique that gives us full field velocity measurements. So with this, we capture all of the essential information that drives the fiber alignment kinetics. And one of the outcomes of this is that we're able to identify really unusual and surprising transitions in the fluid dynamics of
Good afternoon, everybody. I will be presenting on SARA, a multi-university collaboration focused on accelerating materials discovery through a combination of high-throughput experimentation and artificial intelligence, with an emphasis on the construction of these processing phase diagrams you see here on the right, which yield information and insights into the synthesis routes and formation of metastable materials. SARA has complete control over our thin film processing method, lateral gradient laser spike annealing. The data from each of these experiments is analyzed via micron scale analytics, namely the micron focused X-ray diffraction at the IDB3 beamline for spatially resolved phase information. This is piped back into SARA, which does some active learning to rapidly construct these complex phase diagrams in the most efficient way possible. So if you would check out my poster, you can see how SARA works, what it's been accomplished so far in future studies.
Hi, this is Detlef Smirgis. I'm a visitor in Mark Pollock's group at Binghamton University. And I'm gonna talk about a new buzzword that's going around in the electronics community, flexible hybrid electronics. So flexible means that things are printed on flexible substrates, meaning plastic foil essentially. Hybrid means that we want to combine these flexible substrates with silicon-based integrated circuits. And on the right of my little slide, you see one of these examples. And the key part here is the interconnect that connects our substrate materials with the integrated circuits. And I'll tell you more in my poster.
Hello everyone, my name is Jinran Feng from the Cornell University. My poster is going to be focusing on the operational X-ray characterization of copper sulfate as the anode material for lithium-ion battery. Copper sulfate is a promising anode material for lithium battery because it has high capacity and energy density. It also has high electric conductivity and low cost. But one problem hindering from commercialization is that it does not work well with carbonate-based electrolyte and commercialized lithium cobalt oxide cathode material. Therefore, our group have developed a method to synthesize carbon wrapped copper sulfide, which successfully prevents the side reaction between copper sulfide and carbonate-based electrolyte. So we have used spectroscopy to study the mechanism of copper sulfide in both carbonate-based electrolyte and ether-based electrolyte. And we also use diffraction to study the activation process of the carbon wrapped copper sulfide in the carbonate-based electrolyte. Thank you.
Hi everyone, my name is Louise Debev. I'm Louise Debev. I'm a postdoc here at CHESS. Accidentally got muted. And I'm interested in catalysis, and in particular platinum catalysts, and I'm trying to understand why they work so well so that we can make them use less platinum, or maybe even make something similar using a different metal. And to do that, I've been using a technique we have here that's called X-ray emission spectroscopy. And it is typically used for first row transition metals such as iron. But I've been trying to apply this to platinum to see if it works. And I have been getting some cool data that shows that it does work. So if you're interested in that, please come see my poster and come to the rest of the spectroscopy session.
Hi, my name is Anuj Bhargav, and my research focuses on developing a new model of charge transport in spinels. So spinels are a class of material with a lot of exciting electronic and electrochemical properties. However, the integration of spinels in devices such as batteries and supercapacitors has been limited because of its low electronic conductivity. So in this work, I first determine how charges flow in spinels. Then I highlight the limitations of the old charge transport model, which was developed in the year 1961. And then finally, we develop a new model. So to develop a new model, we grow single crystal thin films of manganese iron oxide using molecular beam epitaxy. We do a lot of X-ray and electronic characterization, and then finally using DFT, we correlate the structural properties to the electronic properties. Using this, we come up with a new transport model and a new conductivity equation, which we show to be in excellent agreement with the experimental data. Thank you.
Hi everyone, I'm Mario Ramos from the University of Puerto Rico. Hydrogen production can be accomplished renewably by coupling photovoltaic devices with water electrolysis systems. However, the efficiency of these devices is hindered by the sluggish kinetics of the oxidative half reaction known as the oxygen evolution reaction, or the OER. For this reason, we need to develop better OER electrocatalysts so that these devices have lower energy losses. In this work, we use zirconium phosphate nanoparticles as support for transition metals as OER electrocatalytic systems. At the poster session, I will discuss previous results and how X-ray absorption measurements taken at the photon in, photon out beamline have helped us in understanding how these electrocatalytic systems behave in operando conditions.
Hello, my name is Blair Liebert from the University of Toronto, and my poster discusses our group's latest work on studying iridates on the PIPCOX beamline. In particular, we studied strontium iridate, the well-known spin orbital Mott insulator. The structure and magnetism in this compound is very similar to the cuprate LCO, motivating many doping studies. Nonetheless, no bulk superconductivity has been achieved to date. In particular, we looked at doping with rhodium, which has many conflicting reports. To gain more insight on the effect of rhodium doping and strontium iridate, we studied it with Herft X-ray absorption spectroscopy. Here you can see two different resonance maps measured on our compounds. If one detects absorption with the total fluorescence, basically a projection of the intensity on the x-axis, the spectral width is large due to the lifetime broadening of the 2p core hole. However, if we look at a single emission energy, we can reduce this effect and achieve finer detail, such as you see here for two different rhodium doping levels.
This is the case of the dog that didn't bark. The modern theory of electrons and photons, namely quantum electrodynamics, predicts that there should be a continuous spectrum of photons diverging toward the infrared to lower energies if a photoabsorption event occurs. That is, an incoming photon produces a photoelectron. That spectrum, which is tough to observe because it's weak, has been claimed to be much greater than theory for such an experiment in earlier work. However, the nuclear experiments suggest that it's consistent with theory. We have performed such an experiment here at CHESS, and we get the case a surprising result, namely, we see a much weaker signal than expected. Come see our poster and see how we did it, and you judge for yourself.
Hello, everyone. My name is Joseph Soto. I'm from the University of Puerto Rico at Rio Piedras campus. Today, I'm going to be presenting to you a work done at PIPCOX beamline at CHESS, where we were evaluating a platinum nickel nanowire catalyst for the oxygen reduction reaction in alkaline medium. The problem is that common fuel cells use acid electrolytes, and alkaline medium has demonstrated that it's a good alternative to replace these acidic fuel cells. In this work, we're going to present to you some operando experiments showing promising results as to why platinum nickel nanowire catalyst can be potential catalyst for these types of fuel cells. Hope to see you everyone there. Thank you.
Hello all, my name is Ben Martin. I run the R&D group at Sidor Technologies. I'm going to be talking to you a little bit about the ultra wide dynamic range MMPAD and the need for it in the presentation later. As the light sources get better, the detectors need to keep pace and have not to date. So I'm going to be talking about where we currently are with the detector system, its features, and performance metrics, and then where we're going with the technology and what's next, what we're currently working on. I also like to point out after me is a colleague at Cornell, Kate Shanks, who's going to be talking about the KECPAD and some of the work that we've done with that as well. Thank you.
Hi, I'm Kate Shanks. I'm part of the Cornell Detector Group. I'm going to be talking about the KECPAD. It's developed here, recently commercialized by Sidor Technologies. So it's a photon integrating area detector capable of single bunch imaging at storage ring sources like chess with down to 100 nanoseconds interframe separation. So this kind of burst mode operation opens up exciting possibilities in terms of studying dynamics in warm dense matter, crack propagation, shock wave propagation, and so on. So I'll show results from a recent suite of demonstration experiments using the KECPAD, including bunch train resolution at chess MSNC, using a version of the detector equipped with a CAD Telluride sensor suitable for use with high energy X-rays. Thank you.